let's just finish off this topic. How come you moved that promotion?
Yes.
Just one more row. So we were discussing the two special cases where you can integrate that equation. Which equation? Then you might do because you had lunch between the two classes and lunch tends to make you forget something. So that is the equation. So gazebo, in order to find out where the robot is, it's actually doing this. It's integrating here, xi dot and yi dot and theta I dot. Now, I told you that there are integrals that cannot be completed mathematically, whereas you can always differentiate. So therefore, you have to do numerical integration, which is quite common these days with computers. So I said there are two cases for which there is a closed result, like the nice mathematical result. One of them is robot driving straight, which is not very useful, but I thought since the integral is easy, it's good to put down the result. And what we get is the standard y equals mx plus c form of for a straight line. And essentially, you point the robot in a certain direction, it can only go on the line, or it can go backwards on the line. So not very useful for robotics because it's not able to explore the entire area. The second one is more interesting. It's actually useful, even though you might not think so initially. And that is, if you assume the two wheel velocities, now let me point out, here the two wheel velocities were the same, and so you get 0, and integral of 0 is theta naught. But next, we assume that we have two different wheel velocities, but they're constant. So that should produce a circle from all the discussions we've had so far. So, in fact, it does. So, theta dot t, the third equation, is v1 minus v2, with v1 being a constant, v2 being a constant. And you can integrate it now. Theta of t is v1 minus v2 by 2l times t plus theta naught. Now, how did I get this? It takes about 2 pages of integration. You can integrate it. I know the first time I did it in class, the students almost, ran me out because it's quite intense, but it can be done. So I stopped doing it. I just get the results these days. So let's look at the result. X of t is initial position plus some coefficient which is constant because n is constant, v1 is constant, v2 is constant, v1 is constant, v2 is constant. So here v2 is not equal to v1, otherwise we'd have trouble, right? Dividing by 0. But we already covered that separately. That's the straight line case. So over here we have constant minus constant over 2l times t plus theta naught minus sin, this is the constant, sin theta naught. Theta naught is the initial heading. Similar expression for y, except that sine is replaced by cosine, a minus replaced with a plus, and a cosine for sine. And this one is a straight integral of that. So here, so theta of t, theta dot of t is also omega. So theta dot of t, you can put equal to omega because it's the same thing, and that's what we get for omega. Okay, now let's see why I said that this is actually quite useful. It's because a circle does not have to be driven forever. You can drive small pieces of a circle. And if you realize that, you will immediately realize that that is the basis of the geometry equation. I'll show you, that's the next slide set. But let's first find out this mysterious coefficient. What is that? So I pulled it out, right? Now, that in fact happens to be, so by the way, why is this a circle? I forgot to mention, this is the parametric form of the circle. We're used to looking at the circle as x minus x naught whole squared plus y minus y naught whole squared is equal to r squared. Yes, that is the more popular form of the circle. There's also a parametric form of the circle. You won't look at this and say, oh, that's it. So let's go to this website. Okay, it's popped up here. So I've got to move it to the other screen. One second. Okay. So this is x is equal to 20 cosine t, y equals 20 sine t. Literally, x is equal to 20 cosine t, y equals 20 sine t is being applied. And it is a circle. In fact, you can drag this. Drag it? Yeah. So all the different points on the circle are generated. So you see here 20 cosine 54 degrees, 20 sine 64 degrees. Those are the two equations, right? And it's given to you. In fact, it's quite a nice website because you can set it to not freeze the radius, and then you can pull it out. See here? This number is changing. So that's the radius, right? See? That number is changing when I put it in and out. And our equation also has a similar form. Yeah, you're saying that it's much more complicated here. I'll get to that in a second. But essentially that number here is the radius of the circle in the parametric form. So let's go back and look at the PowerPoint again. Okay. Move out of the way. So here's R, the radius. I'm going to show you why it's the radius again in a different way soon. Sine. So basically there it was sine t. Here it is sine of constant times t plus theta naught minus sine theta naught. That does not change anything. It's still a circle. It's a more sophisticated circle, that's all. So even though you saw cosine t, sine t here, it can also be sine of some argument and cosine of that argument. It's still a circle. Alright, now let's take that part and play with it some more. And here it is. See? I divide the numerator by 2 and divide the denominator by 2. Do you recognize the numerator? That is the forward velocity of the robot, isn't it? And what about the rest of it? L, so VR minus VL by 2L, right? I can put the L here if you like. That's omega, isn't it? So that's how we concluded that R should be V by omega. So that's the basis of your homework exercise. And just to remind you, we can achieve an R by multiple combinations of V and omega. I can double V and double omega, you get the same R. So be careful not to let the velocity go too high. However, it's in your interest to get as large a velocity as possible because you want to have it do it quickly, right? You don't want to wait and go and have lunch and it's still working on the L. So you want to move fast. So try to use the highest V so long as it's within 0.4 meters per second, less than 0.4 meters per second. And then you can adjust omega accordingly. Okay, x naught, is not the center of the circle. It is the initial position. So x is based on some initial position and initial heading. Yeah, initial heading. It's not the center of the circle. We already discussed the center of the circle. The robot is going this way, the center is going to be here. The robot is going to go this way, the center is going to be on this side. And you can find that because it's R away on the robot's y-axis, right? So if you're going this way, its coordinates will be 0, r on the robot's axis. You know what I'm saying? Because xr is this way, yr is this way. So if the center lies here, obviously the x coordinate is 0. So 0, r or 0, on the other side. It's still 0, r, but r is negative. That's the way you should look at it. Don't try to put the sign yourself because the algebra takes care of itself. So don't try to fix it because there'll be too much confusion. So r is negative, it flips to the other side. Alright. Yeah, this is not necessary here, and we are done with this. Okay, let's do the second PowerPoint, and then I'll show you a MATLAB program that also simulates a differentially steered vehicle, and then we'll see what we do after that. So let me move this. I think I posted this also. Make sure if not, I'll post it now. The title of this is the part B. This is the part B of what we had earlier. It's the actual odometry equation. So we're just setting up the basics, the fundamentals necessary. Now we're going to actually discuss the actual odometry equation. part B, odometry equation. You'll be surprised at how simple it is, the concept. So first of all, I'm going to display mode, or presentation mode. So first, when you say odometry, it's really localization through something known as dead reckoning. So dead reckoning is the technical term for that. You may have heard that and you may say, okay, who is dead? But I don't understand the basis of dead reckoning. You can go look it up on Wikipedia. It has an explanation for why they call it dead reckoning. But essentially, it's estimating the robot position without using external measurements. So remember, sounds like an eternity ago, but it was just last week. We started on Friday and I gave that introductory talk, and I said there are two ways in which human beings localize ourselves. One is to count steps, right? You're really not, you're not saying 51, 52, we would sound very odd if we went down the hallway doing that. We have a sense of distance, is what I mean. So there is a sense of distance, but it's imprecise. It's not accurate. If I counted 100 steps, multiple times, I would end up in slightly different places, right? Because I may take a shorter step or a slightly longer step, right? So then we're constantly surveying the surroundings, right? That's the equivalent of GPS. So localization typically combines these two together. It synthesizes the odometry. Odometry is like counting steps. So a machine, there's no such thing as steps. It counts the encoder, the wheel rotation. I'll show you in a second. You may have had it in a prior class, but I'll go through what odometry is in terms of the raw measurements. So you're measuring the rotation, right, of the wheels, and the circle equation. We haven't gone through odometry yet, but there is a potential because every time you're doing a little tiny circle, right? So if you can use those equations to say, if I get this reading here, where would I be? And then you keep on adding to that. Even if the velocity changes, you just say, I have a new circle now. So I do the same thing again. I say, where am I? So if you sample frequently, you'll have such small circles that basically there won't be much error. So that's the whole basis of odometry. Now, because you're using your own internal measurements, it's known as dead reckoning. So dead reckoning means don't use external measurements. Just locate where you are just by measuring some aspect of yourself. That means you're not getting GPS, or you're not looking and saying, okay, there's a Udupi restaurant. I know where that is, so I must be here. Right? So the external measurements don't count. You have to do it purely from your, without the help of external measurements. So there are problems because the wheel slips. So you may not know this, but when I'm walking, not just me, but anybody, when you're walking the hallway, there are small, tiny micro slips. You don't recognize it. So if somebody had put water on the floor, there'll be a little bit more slip. So the same thing happens to robots with wheels. Because based on the roughness of the surface, even though visually you can't see anything, there are little tiny slips going on. And so that's adding to the odometry error. That's why you can't depend upon odometry for too long. You have to get that external measurement, GPS, or you cite something that you know, like a familiar restaurant. If you don't do that, odometry will eventually get you lost completely. You'll be completely lost with odometry. So that's an important step to combine the two. It's done using a process known as Kalman filtering. We'll get to that after the exam week. So if you have the two tires at different inflations, right, you'll have a problem, right? Because we are assuming that they are inflated the same. So then the odometry is going to fall apart much quicker. If one tire is overinflated or underinflated with respect to the other, then the odometry will need refreshed more often. If there is slip, you'll have a problem. You'll get lost. Inadequate resolution, I'll explain with respect to the next slides. Wheel misalignment. Maybe the robot has taken a hit on the side. One wheel is pointing a little bit inside like this. Right? That's also a problem because we are assuming that they are completely parallel. And in a real robot, there's no such thing as completely, maybe a new vehicle. But after a while, if it hits a bump and takes damage, then even regular cars have to be aligned once in a while. So the same thing with robots. So you can use an IMU instead of the odometer. When do you use it? It's for a skid steer vehicle. For the skid steer vehicle, counting the rotations of the wheel won't work very well because it's skidding each time, and that's going to throw off the odometer. The interesting thing is, for a vehicle that rolls, like a differentially steered vehicle, you can use both. By the way, what is IMU? I'm sorry. So IMU is an inertial measurement unit. So basically, it has an accelerometer. So you must have taken a sensors class. You know what an accelerometer is? It measures the acceleration in the 3 directions. So meters per second, right? So theoretically, if I integrate acceleration in this direction, what do I get? I get velocity in this direction. Similarly, I can get velocity in this direction, and if I'm a drone, I'm also interested in velocity in this direction. So I get the velocities. If I integrate once again, I get the position. So it's a substitute for odometry, does not work for skid steer vehicles. So if you're really worried about accuracy, you put an odometer as well as IMU. And then you find a way of combining them. Again, Kalman filtering. You can't just say, okay, I'll average it, because only if the two accuracies are the same can you average it. If they are not, you have to do some kind of statistical average, and that's what Kalman filtering is. You'll find out after the break that you have to average them in a statistical sense. So now you have IMU, odometer, and then you have GPS. So now you have to synthesize all of those 3 together. And that's how any commercial vehicle localizes itself, including self-driving cars. For self-driving cars, it has to happen very fast because you might be going at 70, 80 miles per hour. So everything has to happen much quicker. You can't say, give me 5 minutes, I'll give you the result. So that's the IMU, inertial measurement unit. It has the accelerometer in this direction, this direction, this direction, and 3-axis accelerometer. Okay, I promised to tell you what that inadequate resolution is. And that's why I found this diagram that captures what an encoder is. So imagine this is the wheel of the differential drive robot, one wheel. The other wheel will similarly have an encoder. So it's basically a disc that is attached to the wheel with alternate black and white sectors. So there is a light source here and a light pickup on the other side. So anytime the black part lines up with the source, it's going to block the light, and anytime you have the space in between, it's going to allow the light to go through. It's going to be picked up by the sensor, and so you're going to see something like this, right? After cleanup, you see a nice pulse wave. Do you realize that if you go faster, what will happen to these pulses? They'll get compressed, and if you go slower, they'll elongate, right? That's it. You're just getting a microcontroller to count these. Now, why do you have a beat? If I did not have a second channel, then I can only tell the speed of the wheel, but not whether it's forward or backward. So now I see A and B are slightly displaced. So look at B. You're getting the pulse here, where A is not high. So by comparing which one is ahead, you can figure out whether it's going forward or backward. So typically you have at least 2 channels. We actually have more channels. You can do a lot of things with this. This is the simplest encoder. So I said wheel resolution, right? How many of those black and white sectors would you like to have so that there is 100% accuracy? It will have to be infinite, right? But there's no such thing as infinite. Okay, now how about 10,000? There are encoders with 10,000 of those sticks all the way around, by the way. But the problem is there are other issues. So there's no point in loading up here, right, saying I'm going to be more accurate when a little wheel slip is going to destroy all that. So you only have to have as many as you need, because if you have a very dense encoder, then you're going to have to process it. Your microcontroller will have to be faster because you're going to get more of these square waves per second. So there's no point in overdoing it when you have other issues, right? So that's the point, that you have to pick. 1,000 is very good. Imagine a tire, right? And you put 1,000 of those. That's a little piece of tire, very small piece of tire. And you can assume it's doing a circle, right? Between one of those and the next one, you can assume that the robot is doing a circle, and it's fine. It will work. So that's the beauty of the circle equations. Now, the exact odometry equations are right here. So I want to remind you here that delta SL, okay, delta SL is how much the left wheel goes through the circle, right? Delta SR is the same thing for the right wheel. We are turning left, so delta SR is larger than delta SL. And the midpoint is somewhere in between. So this is the change for the midpoint. It's distance now. We are assuming that we are focusing on a small tiny circle. So we're going to take an odometry reading here, and then we're going to take an odometry reading here. And then we're going to figure out where the robot is. It's so simple actually. So if delta SL is this, do you understand this? So here is radius. This is not capital L. Capital L is between these two. This is lowercase l. So R minus L times delta theta is delta SL. So there it is. Similarly, R plus L times delta theta is delta SR. The amount by which the midpoint moves is the average of the two. Delta SR plus delta SR by 2. And as we derived earlier, delta theta, the change in the angle, is the difference, but this time you have to divide by 2. I'll just see from these two equations, you add and subtract. When you add, you get this, and you subtract, you get this. So this is the delta theta. Now, this is the key part. So, odometry is relative. That means, from the previous reading to this reading, delta SM, right? I can't read delta SM, because there is no encoder for delta SM. But, there is an encoder for delta SR and delta SL. You agree? Because that's what that disk is measuring. So, I put the right reading, just the change, because you can't go back to the beginning of the first circle. You have to go back to the beginning of the current circle. Right? And then, for the next circle, you start again, as if you started here. Right? You can't start from the first time when you got the robot going. So, each time, you measure delta SR, delta SL divided by 2, you got delta SM. And then you measure delta SR, delta SL, subtract the 2 and divide by 2, and you got delta theta. So you got those little delta SMs and delta theta. And that shows you how much you have turned and how much you have moved. Okay, now. So here it is. So all I've done is, I've taken x0 to the other side. Remember I said it's only for this circle, how much you have moved. So delta x is x1, the new position. This is the new position, meaning, let me show you. That's x1. This is x0. I've got delta Sn, right? From the encoders. I've got delta theta from the encoders again. So this equation tells me that whatever angle heading, so whatever heading I had before, you add what the encoders told me I have done since the last reading, subtract sine theta naught, that was the previous heading, and there it is, an equation for how much you moved, or you can write this as an equation for x1. So basically you don't want to write like this, you want to, I don't know why I did that, x1 you want it to be on one side. So each time you can measure or predict where you are, x1 by 1. You can't do it forever, because I told you, there'll be slip, there'll be other problems, you may hit a bump, and if the wheel rises and it spins, then what does that mean? You're not turning, but by looking at the numbers, you'll say, I did turn a lot, right? So that's why GPS or some other way of correcting yourself is needed periodically. Okay, so we're at the end of this. So what I want to do now is I want to show you a program. I may have put it on Teams. It's called Learn Diff Drive Model. If not, I'll put it up there before discussing it. Can you check on Teams? Let's see. I thought I put this there. It should be the same directory. So kinematics and control. Yeah, it's there. Learn Diff Drive Model. It's the only M file. So it's the only M file in that directory. So if you have MATLAB, you can run it along with me. But it might be useful to you in your assessment exercise 1. So let me close this now. I'll give you a few minutes to set up if you want to work with me.
Shall we open draws as well?
No, you don't need draws for this. Yeah. So there's the cleanup command. For those of you who are Hindus, you'll understand this. You go to the temple, and everybody will understand it, right? In the context. So you got to do this in MATLAB all the time. So clean up, and then I bring in this. So you can go to the MathWorks help page, and you can say differential drive kinematics, and then it will give you a help file. So I'm just giving you a quick advanced help file on that basically. So this is I'm creating an object. I'm creating an object called kinematic model, and I'm using the master to create it. Now, if you read the help file, it will say, okay, what is the initial state? Initial state means what do you want the initial x, y, theta to be. So I'm saying 0, 0, 0. You can make it anything you want. Okay? Then, so what it's going to do is, it's going to use, remember I said numerical integration? Well, ODE 45 is one of the popular numerical integration programs in MATLAB. So it takes the kinematic equations, right, and integrates them to produce the x, y, theta as a function of time t. Now, for the circle you don't need it because the circle has an equation, right? But they don't know that. In general, you just get points, right? Because you might have a little circle here, another circle here, another circle here. In fact, your L is many circles. It is in fact 7 or 8 circles, depending on how many segments you want to put. A real driving path is, you can't even count, because it's really tiny circles, right? So you have to do it with the solver. Even though equations are available for those little pieces, it's better to treat it as something that cannot be integrated and just integrate it. So that's why they're using the ODE 45. Okay, here it is. You see? So look at what he's doing. The solution is already available. The kinematic model is in solution form, but because he wants to use the integrator, he's taking the derivative. This is a MATLAB operation, by the way. He's forcing a derivative on this so that you can use the numerical integrator. It's like going like this, right? But that's the only way you can do it if you're going to constantly integrate and you have little tiny circles. So you can't use equations at that point. It's not worth it. So here it is, derivative of the kinematic model, and if you go look up the help file, you have to provide these other inputs. So what are the inputs? So here it is. So why did I comment this out? It's because the default option for this program, the default option is for you to provide the 2 read speeds. So the default option is to provide phi L dot, see that is phi L dot, remember? Phi L dot left wheel dot, which is the spinning rate of the left wheel, and phi R dot is the spinning rate of the right wheel. That's a very odd thing to provide for somebody who's driving a robot. I told you, d omega is the commonest, easiest way of driving the robot. A customer doesn't care, right? If you put somebody on that wheelchair with a joystick, what does he know what the individual wheel speed should be? He just says, go forward recorded the speed, right? This indicates the speed you want, and that indicates turn. So that has to be decoded and given to the motors. So I thought that was an unnatural way, 50 radians per second, 40 radians. So instead, I said, take my inputs in this form. See, kinematic model dot vehicle inputs. I want it to be vehicles, speed, and heading. So this is MATLAB says if you put that, yeah, you can give me V and omega. So I gave it 1.5 and 1, and you know what the radius should be, V by omega. So 1.5 meters, right? And the circle should be diameter 3 meters. Okay. So I picked time of integration. I think I picked it so that it's a full circumference, but I could be wrong because I was playing around with the numbers last night. But I used, so you're wondering 2 pi, because it's easy to calculate. You know, MATLAB has pi, MATLAB recognizes pi. So basically, I think I picked something so that it does one full circle. I could be wrong because yesterday night I was playing with it and they had left it at some point where it doesn't do a full circle. Maybe it does less or more, I don't know. And then I get the time and the y, and then I plot. So by the way, it's not y and x, because what they're using is they're using a single array. The first column is x and the second column is y. So don't get confused. They don't use an x and y. X is for something else. I don't know, there's no x at all. So x is not at all used. And y contains both x and y. And then I plot the path here. Oh, very simple plot. Okay, let's run it. Hope it doesn't crash. Oh, the plot is here. And there it is. So you see, 0 and 3. So 3 meter diameter, 1.5 radius. Now how about stopping it less than a full circumference? So I'll close this and say maybe 1.5 pi. And then run it again. Now you know why it looks like an egg? It's because you have to force MATLAB to use the same scaling factor this way and this way. Otherwise, it has some internal algorithm that it uses. So that's why it looks like an egg. It is a circle, believe me. Because look at it. It's going from 0 to 1.5 and then from 0 to 1.5. Sorry, 0 to 3 because it's going from minus 1.5 to 1.5. That's 3, right? Minus 1.5 to 1.5 and 0 to 3. So it is 3, but it looks like an egg because that's how they choose to plot it. So you can play with it. You can see it's stopping short now. So how is this going to be useful for your air? So you can try it out here because you have to figure out how to give it different radii, right? Because once you figure out what your radii are going to be, right, then you have to modify this program as follows. So go to the help file and see how you can put consecutive inputs. It's possible to do that. So you have to give it, because you'll be changing omega, right? I think it's a good idea to keep V fixed and just change omega to get the different radii. Don't forget, omega has to be negative to go this way. So you can put all those things together, put it in a loop, and get it to do the integration. The integration will be for each circular segment. And then you repeat it within the loop. You give it a new input, this input. So it has to be in a loop, for loop. And then the L will be traced out. So then the only thing you have to do is go and implement it in with a real, not a real robot, but a simulation robot, which is better than MATLAB. There's no robot here, right? If you do it with the Turtlebot 3, you can actually put the real Turtlebot 3 and it'll do an L. That is the beauty of that. It's real. Here, it's all software. Is that clear? Okay. Now the last thing I'm going to do in the time we have is to remind you of what a control loop is. So you probably had a controls course, or maybe you haven't, but remember the controls is going to be done through the next assessment exercise. So before the break, I'm going to refresh your memory on control grid. So, you know how to slow it? Okay, so there is some form of control that came before closed loop control, and that is open loop control, right? So in the old days, you have a house and you want to have a certain ambient temperature within the house, right? So you go set the heater to a certain level and the house will reach a certain temperature. The problem is, if you do it that way, it's called open loop control because you should really be measuring the current temperature, not setting it to a certain position on the dial. Because what do you think will happen if you're in a different season? Let's say that you're not in summer but you're in winter. Let's say it's an AC, right? Then in summer more heat is going to be coming in from the outside. And that one setting of the thermostat is not going to do it, obviously, because that's called an open loop control. So typically you don't have a control system. Well, open loop control is not really a control system. That's my point. You don't have a real control system unless it's closed loop. And closed loop means you must sense the current temperature and accordingly automatically change the inputs. So the heater setting or the AC setting should change automatically, right? So how is that achieved in practice? It's actually quite simple. The simplest control loop looks something like this. So you have the system, which in our case is the robot, and there is some output you're interested in. So it could be speed. So let's assume speed because everybody can relate to that. This is just the forward velocity. We want, but simply speaking, you should have a control loop for the right wheel and the left wheel, right? But we know that. So you have to, in practice, the implementation might be slightly different. Let's assume that we're just controlling V. So you have to sense it. And then out here, you have an input, which is the desired velocity. So this is what you want, right? This is what you have. So maybe you can call this actual. So this is what you have, and this is what you want. And so you take the difference, not the sum, and so you get an error signal. And then you use the error signal to drive the system in such a way that the actual moves towards the desired. If it moves away from the desired, that's called an unstable system. Because, so if I do this, if I make a mistake and do this, then you have a problem, right? So you have to find the difference, the error or the difference between the two. So this is any control system. Now how does this work in the case of your the robotics exercise that you're going to do next after the break? So let's I'm giving you a preview of the next assignment. So here is a triangle, right? An equilateral triangle. Let's say each side is 3 meters. You know that for an equilateral triangle, each angle will be 6 degrees. So the robot is starting here. And I want you to navigate the 3 sides. This is the actual turtlebot 3 which is going to do that. This is an interesting learning experience, by the way. So, how are you going to go about doing this? Now, at the most elementary level, you'll say, okay, it's pointed at the next vertex. So I'm going to set a velocity, maybe 0.4 meters per second. Right? And then I'm going to drive it so that it covers 3 meters. Because I can calculate D as 3 meters by V, right? And so I'm going to monitor, I'm sorry, this will be time. So this is the time taken to traverse this side. So I just look at time. We already, remember we already, we know how to monitor time. We're doing it in the circle program, right? So I'm going to drive it for as long as I think it takes to go through 3 meters. Just try it. Well, because I'm going to give you this part of the program, and then you're going to build on it. And you will find that every time you do the triangle, you get a slightly different triangle. So by the way, I haven't finished. So when you reach here, right, you will notice that the robot is not here or here. It may actually be here or here. And that is because Gazebo has two problems. One is the turtle bot 3, for whatever reason, they have not used the right values for the inertia of the wheels and the structure and so on. There is a problem with it. So even when it's sitting still, after a while if you watch it, we're doing this. It starts spinning slowly. It does it on its own, and so it's a known problem. It's already reported on GitHub, and they have fixed it for the next version, the Ubuntu 22.04, which is Foxy, right? They have fixed it. Now, if I had time, I would go and copy whatever they have fixed into the files for the Noetic, but I haven't done it yet. So, how do you cancel that? There is a way of, remember the thing that did not work, which was set model state. So what I suggest is in the MATLAB program, just before you're ready to let the robot run, set it so that it's pointing this way again. So even if it has sort of jittered and it's facing this way, because otherwise you'll be going the wrong side of the triangle. You may even be going away from the triangle, so you can set the model state. But that's a problem of the software, right? And not having the right weight for the different components. But the fact is, Gazebo also introduces some noise, so that when you do multiple runs, in one run the robot will end up here, one run will end up here. There is something they are adding as noise to make it realistic, like a real robot. So therefore this is not going to do it. So if it stops here, it's because the 3 meters is being measured this way, right? So now when it turns, it's going to go like this. And so you'll find that this triangle can never be closed if you base it on the time taken to drive through each side of this triangle. So hold that thought. You have time, right? Okay. The second thing is, when you get here, you won't get there, but let's say you get here. What are you going to do now? You're going to turn through 60 degrees. So how are you going to do it? You're going to say V is equal to 0, because I want to stop and turn, right? I don't want to turn on the move. It's a little bit complicated at this level. So I stop and turn, I set an omega, and then I say, how long will it take with this omega? Suppose I set omega as 60 degrees per second. How long is it going to take? 1 second, right? You don't want to make omega too high, because when you speed up, then you have more time, stopping when 60 degrees has been covered. So you really want to make it a little bit less. And then you want to turn until 60 degrees has been gone through in terms of change in heading. Now there's a problem there. Because again you're going to use time. You're going to say it takes me, turn time is 60 by whatever omega you chosen. So again you're going to measure time and say, have I crossed the time, have I crossed the time, have I crossed the time, and then you're never going to hit the exact time, right? You realize that. It's going to go over always. Now if you're going very fast, you might go over a lot. Right? That's like driving. If you want to stop, you typically slow down before you get there. This program is not so sophisticated, so no slowing down, only one rate. 1 omega and 1 v. So you find that the angle of 60 degrees is not repeatable. Next time you run it, it might give you 58 degrees. So that's how it works. So that's really an open loop system because you are not measuring what you should be measuring. What should be measured? You want to get to this node, right? This is the node you want to get to. So the first thing is you want to measure the distance to this node. How do I know where the robot is? Odometry. Odometry. So you have the two positions. You have the robot position and you have the first vertex. Let's call it xy, y1. So you know xr minus x1 squared plus yr minus y1 squared square root of. So you're going to measure that. And so you're going to zero it out or else you won't stop. We can't zero it out. You know what I mean? In the real world you can't zero out anything. It's either going to be a little bit above or a little bit below. Is that enough? It's not enough. Because if you're not pointing to this node, it doesn't matter because after a while, so basically you're going to say, I want to be inside the circle, right? You can't be exactly at that point. It's not possible. You're going to say, you're going to define a narrow circle and say, I want to be inside the circle, and then I say, I have reached that vertex. But because of the orientation error, you're going to have a problem because if it's not pointing into that circle, some part of the circle, it will just go right past this and you'll never be able to find so by the way, you're not doing time anymore. You're saying, I won't stop till I get into the circle, right? So time, the old method is gone because that's useless. But it's not enough to just do distance. Constantly you're going to have to correct and point towards the next vertex. And how do you do that? It's because you have your odometry. So you know your current rating, you know where the vertex is, and therefore as you're driving to kill the distance, kill meaning use up the distance, you're going to always point. So you'll be going like this. Hopefully not like this. No? If you overcorrect the control system, you'll be going like this. But you need to point at the vertex at the same time go towards it. And magically you'll find that the triangle now negates itself. Otherwise, you will always get what they call, like for flights, they call it an open job. So you will get a triangle that is open. No matter how many times you run it, you might get lucky. And students often have got lucky and said, hey, you said this is not possible, but here it is. And then I say, okay, then let's run it again, and it will fall out again. So this is a very interesting exercise. It's a little bit more difficult. I'm going to make it easy by giving you part of the code. I'll give you the code for time-based, going around the triangle, and you can then set up the distance and alignment loops. So there are two loops. There's one loop within another loop. There's a distance loop and there is a alignment loop. By the way, that's how you drive, right? That's exactly how you drive. How do you stay in a lane? You're constantly correcting while you're going forward towards your destination. So it's very much like driving. So we'll get to that after the break. Okay. I'll stop here. Yeah. Have a good vacation. I was joking. Okay. Good luck in the exams. Okay.